Welcome to Efiwe, excellence without stress.
Hi, welcome back, my very smart, brilliant, awesome Efiwes. And today we are back again. And today on this our very interesting journey, we are going to take the topic electromagnetic induction. Electromagnetic induction. You know me, I'm still your favorite tutor, Miss Stella. And today I'm going to explain everything about electromagnetic induction. And even hearing the title, you already know what it's about: electric and magnetism. Electric and magnetism, inducing electric through magnet. So that is electromagnetic induction. So this is a negative charge, and so today we are going to electromagnetic induction. We can see this is a coil or loop, and this is a magnet. So what is happening when this magnet was brought close to this is a galvanometer. We already know what a galvanometer does. A galvanometer is able to detect very small current. So what was noticed was that there was a deflection, and that is what this class will basically be all about. Electromagnetic induction. Michael Faraday, 1791 to 1867, made the great discovery in 1831 that an electric current could be produced in a conductor under the influence of a varying magnetic field. This is a magnetic field. You already know that all these magnetic fields are just imaginary lines around either a magnet, imaginary lines around an electric field where the electric field is mostly felt. So Michael Faraday made the great discovery in 1831 that an electric current could be produced in a conductor under the influence of a very magnetic field. In one of his experiments, he wound two coils A and C on a steel ring. You can see it, and observes that when the switch S was closed, a deflection was obtained on the galvanometer, but when S was opened, G showed a deflection in the opposite direction. It showed deflection in the opposite direction. What is electromagnetic induction? Electromagnetic induction is the production of electric current or voltage in a conductor. These are conductors. Whenever there is a relative motion between the conductor and a magnetic field, when this is moving close, you will notice that the ammeter and the galvanometer does the same thing. They detect current. There is a deflection. Said current or voltage in a conductor whenever there is a relative motion between the conductor and a magnetic field or a magnet. That is, its current flows when this is brought, and you can see the deflection here. No current was happening there because there was no motion. You can see the magnet here. This is the coil, this is the magnet far away from it, but immediately this magnet was brought close to where the coil is that is attached to the ammeter. You can see the change in the deflection. It moved towards the side, and also when this magnet is now moved backwards, this deflection will go back. So that was where Michael Faraday discovered the electromagnetic induction. That is the production of electric current or voltage in a conductor whenever there is a relative motion between a conductor and a magnetic field. Current will flow in the galvanometer whenever there is a relative motion between the coil and the magnet. There is such relative motion when the magnet moves towards the coil or away from the coil, and when the magnet is stationary but the coil is moved. Such a current is called induced current, and the phenomenon is called what? Electromagnetic induction. It is called electromagnetic induction, inducing current from magnets, and that is electromagnetic induction. The induced EMF or current depends on 1. The speed of motion of the magnet. It depends on the speed of motion of the magnet or the coil. The faster the speed of the motion, the larger the induced current. You see that the faster the speed, the faster you move the magnet, the faster the speed of the motion, the larger the induced current. 2. Numbers of turns. This is what is called the turns of the coil, and the presence of soft iron core inside the coil. Soft iron coil, presence of soft iron core are what the current or EMF depends on. The direction of the induced current reverses when the direction of motion of the magnet or the coil is reversed. I think that you understand that. Look at it. This deflection, if you bring the magnet close to it, it will come like this. If you take it away from it, it will go towards the other side. So let's check. When the magnet is at rest, that is, nothing is happening here, there is no deflection in the galvanometer when the magnet is just staying on. So when you move the magnet towards the coil, the galvanometer is the deflection of in galvanometer in one direction. When magnet is now held stationary at that same point, no deflection again, it will stop where it is. Magnet moves when you move the magnet away, deflection in the opposite direction. If the magnet was here before, now that you are moving the magnet away, the deflection will come towards this side. And when the magnet is held stationary at the same position, no deflection. Is that motion, the moving. If you don't move the magnet, there will be no motion. But once you move the magnet, there is what? Deflection. There is deflection showing the presence of current, because this one is galvanometer detects current, ammeter detects current. Primary and secondary coils. Another method of producing and observing induced current is through the use of two coils close to each other, one of which is connected to a battery and the other is connected to a galvanometer. You can see that one is connected to a battery. This is the battery. Remember that the longer line is the positive terminal of the cell, the smaller part is the negative terminal of the cell, and this is the galvanometer. So another method of producing and observing induced current is through the use of two coils close to each other, one of which is connected to a battery and the other is connected to a galvanometer. The coil A connected to the battery and key, in which the current is made to flow directly from the battery, is called the primary coil. So this is the primary coil and this is the secondary coil. So the coil B connected to the galvanometer, in which current is induced, is called the secondary coil. So this one connected to the battery is called the primary coil, and the other one is called the what? Secondary coil. A current is induced in the secondary coil whenever the circuit is connected to the primary coil is made or broken. A current is induced there. The galvanometer in secondary coil shows a momentary deflection. It either moves to the front like this when the current is started, another momentary deflection but in opposite direction when the current in the primary coil is cut. When you open the key, the deflection will come towards this side, and when you close the key, the deflection will come towards this side. That's what it's trying to say. No current is induced in the secondary coil when a steady current flows in the primary coil. No current is induced in the secondary coil. When a magnet is near a solenoid, this is a solenoid, we say the magnetic lines of force or flux which spread out from the magnet links the coil of the solenoid. It links the coil of the solenoid. These magnetic lines of force move whenever the magnet moves. They move whenever the magnet moves. We say that an induced current is produced in a coil whenever there is a change in the magnetic lines of force or flux linked with the coil. That is when you say you said induced current is produced. That's when you say induced current is produced. Induced EMF in a conductor, the Fleming's right hand rule. You can see this, your thumb is in the direction of motion. This middle finger is in the direction of magnetic field, and the middle finger is in the direction of magnetic field, and the forefinger is in the direction of, okay, the middle finger is in the direction of current, and the forefinger is in the direction of the magnetic field. Straight Fleming's right hand rule: an induced EMF is produced in a straight conductor when the conductor moves across the lines of force of a uniform magnetic field. The direction of the induced EMF is given by Fleming's right hand rule. If the thumb, forefinger and middle finger of the right hand are held mutually, you can see the way it was held, the right hand, the forefinger pointing to the direction of the field. This is the forefinger. Magnetic field is pointing to the direction of the magnetic field. Then the thumb pointing to the direction of motion. You can see thrust or motion. And then the middle finger will point in the direction of the what? Induced EMF. We point in the direction of the induced EMF or current I. The induced EMF is maximum when the conductor moves at right angle to the lines of the magnetic field. When the conductor moves at right angle to the current of the magnetic field, the induced EMF is maximum when the conductor moves at right angle to the lines of the magnetic field and to the conductor's own length. It is 0 when the conductors move parallel. Don't forget that. Maximum when the conductor moves at right angle, that is perpendicular, but 0 when the conductor moves parallel to the lines of the magnetic field. When the conductor, you know, the conductor is the coil, moves what? Parallel to the lines of the magnetic field. The faster the speed of the conductor, the greater the induced EMF. We've already explained that in the previous slides. Laws of electromagnetic induction. There are 2 laws of electromagnetic induction. We have the Faraday's law and we have the Lenz's law. Faraday's law says that whenever there is a change in the magnetic lines of force, EMF is induced, the strength of which is proportional to the rate of change of the flux linked with the circuit. So that's the law, that's Faraday's law. The magnetic flux of field lines linking a coil depends on 1. The magnetic field strength, the number of turns of the coil, like 1, 2, 3, 4, 5, the area of each turn, how big each turn is. Thus, to obtain a large induced EMF, we cause a coil of many turns to move at a high speed across the strong magnetic field. Faraday's law gives the magnitude of the induced EMF. So then we have Lenz's law. Lenz's law states that the induced EMF is in such a direction so as to oppose the motion or change producing it. So that is what the induced EMF, it is in such a direction as to oppose the motion or change producing it. The Lenz's law gives the direction of the induced EMF or induced current. Thus Lenz's law gives the direction of the induced current or the induced EMF. That's what the Lenz's law does. Consider end pole of a magnet moving towards the face of a coil whose ends are joined to a galvanometer. You can see the galvanometer. The face of the coil will acquire a north polarity. You see it, and when you put N there, this follows from what the Lenz's law. N is coming here, so this end of the coil is going to acquire what? North polarity. The north polarity on this face will oppose the movement of the magnet by repulsion of like poles. Hence, current in the coil will flow anti-clockwise as shown. So the coil, because these two of them will what? Repel. So the coil will flow what? Anti-clockwise. It will flow anti-clockwise. So the north polarity on this face will oppose the movement of the magnet by repulsion of like poles. Hence, current will flow anti-clockwise what? As shown. The current will flow in anti-clockwise direction. If the magnet moves away from the coil, the face of the coil will acquire a south polarity. So you acquire what? A south polarity to oppose the motion of the attraction of unlike poles. Lenz's law as an example of conservation of energy principle. Lenz did not establish his law as a result of experimental observation, but from the conservation of energy principle, which states that energy can neither be created nor destroyed, but can be transformed from one form to another. Eddy current. When a solid metallic sheet e.g. copper or aluminum sheet, swings in a magnetic field, it cuts through the magnetic flux, or field lines, it cuts through it. Look at it now, it cuts through. So consequently, according to Lenz's law, an EMF is induced in the sheet which oppose the motion, the movement of the sheet, and that is about eddy current. Hence, the sheet quickly comes to rest and its motion is said to be damped. Its motion is said to be damped. The induced EMF that brings this about produces an induced current in the sheet. Produce an induced current in the sheet. The induced current is known as the eddy current because it flows in circular paths. You can see the induced current. It's called eddy current because it flows in circular paths or closed loops within the conducting or closed loop within the conducting material, like eddy current in water. Eddy current generates heat in the material, leading to wastage of energy in most electrical devices. That's one of the disadvantages of eddy current. Electrical devices using electromagnetic induction. A machine that converts mechanical energy into electrical energy or electrical energy into mechanical energy is called a dynamo. Don't forget that. A machine that converts mechanical energy into electrical energy or electrical energy into mechanical energy is called a dynamo. When it changes mechanical energy into electrical energy, a dynamo is called a generator. When it converts mechanical to electrical, we call it what? A generator. But when it changes electrical into a mechanical energy, we call it a motor. We call it a motor. Please don't forget that. Let's take that again. When it changes mechanical energy into electrical energy, a dynamo is called generator. Don't forget what a dynamo is. A machine that converts, either is converting mechanical into electrical or electrical into mechanical, is called dynamo. But when it changes mechanical to electrical, we call it generator. But when it's changing electrical to mechanical, we call dynamo. Like in a car, we call it a motor. Generators. There are two types of generator and alternating currents. You know the meaning of alternating current that is not flowing in a straight line, while the direct current is the one that is flowing. So direct current generator, like from the battery, alternating current generator, and the direct current generator. So simple alternating current, AC generator. Structure: the AC generator consists of one, the armature, an armature, a rectangular coil consisting of a large number of turns insulated wire around on a laminated core, the armature, a magnetic field created by curved poles of horseshoe magnet or an electromagnet. Can you see the magnet there? We can see the magnet, the north pole and the south pole. So an horseshoe magnet. Two copper slips, rings R1 and R2, to which the ends of the rectangular coils are connected, and which rotates the armature, Two stationary carbon brushes which are made to press lightly against the slip rings. And that's the what? AC generator, the simple alternating current generator. Principle of operation: when the armature, you can see the armature here, rotates, rotates at a steady speed about a fixed axis, the magnetic field of the electromagnet, it cuts through the magnetic lines of force. Let's say that again. When the armature rotates at a steady speed about a fixed axis in the magnetic field of the electromagnet, it cuts through the magnetic lines of force. As a result, EMF is produced in the terminals of the coil by electromagnetic induction. EMF is produced by electromagnetic induction. EMF from a generator, E is equals to E naught sine WC. The coil of area A rotates in the magnetic field of strength B. So flux through the coil is given by phi is equals to what? AB cos theta. If there are n numbers of turns in the coil, then flux is given by phi is equals to n, because they are saying n number. So if it's 5, it will be 5 AB cos theta. So let the coil turn with a steady angular velocity. Don't forget the formula for angular velocity. Angular velocity is T is angle divided by time. So we are saying change in angle divided by change in t, right? Change in angle divided by change in t. So induced EMF is given by change in what? The phi divided by change in t. So if we put these two together, you remember that phi over t, theta over t is your omega. So taking this and putting it together here, we can call phi over t to be equals to what? Change in t of NAB cos theta, because NAB cos theta is the file. You can see the file here. The file is NAB cos theta. So this is the same thing as this, just changing this file to what? NAB cos theta, and we have this. So NAB cos theta is equals to NAB sin theta using some mathematical rules. Alternating current, don't forget what I said is an alternating current. Alternating current moves forward and backward. It's not like the direct current that just goes. You can see the graph of the direct current just directly. It starts from the positive and goes to the negative. It doesn't go back. But for the alternating current, alternating, as it says, moves forward and moves backward, and that's why it doesn't have a polarity, because you cannot actually say this place is positive or this place is negative, because if it moves like this place, if it's starting from positive, when it's coming back it will become negative. So we cannot really say the polarity. An alternating current is a current which changes continually in direction while passing through a conductor. It changes continuously. It's not like a direct current. Measurement of AC and alternating current can be measured by 1. The hot wire ammeter, or 2. Using the heating. 3. The moving iron ammeter, magnetic effect of current, and using the moving coil galvanometer to which a rectifier is attached to convert AC to DC. This is the extension of the hot wire ammeter. Hot wire ammeter is based on the principle that when a current flows through its wire, it gets heated, and as a result, the length of the wire increases. The construction of hot wire ammeter, a platinum iridium wire AB, you can see the AB is fixed tightly between two fixed ends. AB, a spring fixed at one end. C, you can see the spring here is permanently connected to a thin wire. You can see the thin wire here in the middle of AB. The cylinder can rotate about its axis. A pointer P and everything, the pointer P connected to the cylinder moves along a graduated scale when the cylinder rotates. So let's just go to what it does. The current to be measured is passed through the instruments T1 and T2. This is the period T1 and T2. And the wire AB gets heated due to the current. The temperature rise is proportional to what? I square RMS is equal to the RMS. The length of the wire increases and consequently its tension decreases. Because of the tension in the spring on the other side, the cylinder rotates a little and the pointer deflates. So this is just the explanation of the hot wire ammeter. So moving iron ammeter. The ammeter consists of a solenoid inside, which are two pieces of soft iron, or a fixed piece and a moving piece. The pointer which moves over the non-linear scale is attached to the moving piece of the soft iron, and this is the explanation of moving iron ammeter. What are the advantages of this instrument? It is simple and cheap to make. It can measure both DC and AC, since both soft iron pieces are always magnetized with like poles facing each other whichever direction of the current. The instrument is however less accurate than a moving coil galvanometer, and it has non-linear or non-uniform scale. A moving coil galvanometer on its own cannot measure AC, but when a rectifier is attached to it, this converts AC to DC, which can be used by the galvanometer. Direct current. A direct current DC is one which always follows in one direction, even though it may vary in value. An AC generator can be made to produce current by replacing the two slip rings with a single split ring or commutator, as in electric motor. A split ring commutator is a slip ring that has been split into two segments which are insulated from each other. This reversal occurs at the moment when the coil is vertical, that is when current is zero. When current is zero, the induced current appears in an external circuit always in the same direction. Such voltage is, however, a varying or pulsating direct voltage. It is not similar to constant voltage obtained from a battery. Practical generators. To produce larger EMF in practical AC or DC generators, the armature is constructed with a number of turns in the coil. The coil is wound on a soft iron core so as to increase the magnetic flux through the coil. The strength of the magnetic field is made high as possible. Then the armature is made to rotate as fast as possible. So those are the practical generators. Comparison between this generator and electric generator and an electric motor. If a battery is connected to a simple DC generator, it will run as an electric motor. Conversely, if the armature of the electric motor is made to rotate, it will act as a DC generator. So this is telling us the simple similarities between the DC generator and an electric motor. However, when used in this way, the electric motor produces an EMF and is oppositional in that applied to it. This is called a back EMF. So it opposes the EMF. The transformer. A transformer is an electrical device for changing the size of an AC voltage transformer. It acts to increase or decrease the EMF of an alternating current. Structure. In its simplest form, it consists of two separate sets of coils, the primary coil and the secondary coil. So this is current structure of an alternating current structure. In the simplest form, it consists of two separate sets of coils, the primary coil and the secondary coil. The primary coil is the input winding of the turns of the wire, and the secondary coil is the output winding. The coils are wound around a soft iron core. The soft iron core acts to increase and concentrate the magnetic flux within the core. It is also laminated, that is, it consists of sheets of soft iron insulated from each other instead of a solid block of iron. This lamination reduces loss of energy in the form of heat due to eddy current and induce the core. So that is what the lamination does. It reduces loss of energy. Principle of operation. When an alternating current EMF or AC voltage EP is applied to the terminal of the primary coil P, an alternating magnetic flux is produced in the iron which links or threads the secondary coil. So mutual inductance is the flow of induced current or voltage in a coil due to an alternating or varying current in the neighboring coil. An alternating EMF E of the same frequency as that of the EP is induced in the secondary coil by mutual inductance. The same flux or line of force link each turn of the primary or secondary coils. Hence, the total force flux linking the two coils is proportional to the number of turns NP in the primary coils and NS. Don't worry, you understand it when we put the formulas out. So in an ideal transformer with 100% efficiency, the power developed in the secondary coil is equal to the power developed in the primary coil. So that's what we have been saying since. This follows from the law of conservation of energy. Secondary multiplied by the E in secondary is equal to the current in primary times the EMF in primary. That is, IS and IP are the secondary and primary currents. So this current multiplied by the EMF, don't forget that this is IV is equal to what? IV, and where IS and IP are the secondary and primary currents. So ES divided by EP is equal to NS is equal divided by N. That is, the EMF in the secondary coil divided by the EMF in the primary coil is equal to the number of turns in the secondary coil divided by the number of turns in the primary coils. Don't forget that. So secondary EMF divided by primary EF. All of these are giving us the definition. And number of turns in secondary coil is equal to number of turns in primary coil, and these two are equated to what? To each other. They're equated to each other. So we can also have this: ES over EP is equal to NS over NP, and is equal to IP over IS. Don't forget that. That is EMF of the secondary coil divided by the EMF of the primary coil is equal to number of turns of the secondary coil divided by the number of turns of the primary coil is equal to current of the primary coil divided by the what? Current of the secondary coils. All of these can give us the different formulas for this, for the transformer. Hence, the current in the two coils are inversely proportional to the number of turns in the coil, but the voltages are directly what? Proportional to the number of the turns in the coil. Don't forget that. To use a transformer to increase an applied voltage, that is to make ES greater than EP, that NS must also be greater than what? That NS must be made greater when we find the must be greater than NP. NS must be greater than NP. Sorry, this is a typo. Must be greater than the NP. That is, the number of turns in the secondary must be made greater than the ones of the number of turns in the primary. When NS is greater than NP, then current in secondary coil will be greater than the current in primary coil. Hence, in a step-up transformer, the primary current is greater than the secondary coil, but the primary voltage is lesser than the secondary voltage. Don't forget that. We are saying when the number of turns in the secondary coil is greater than the number of turns in the primary coil, then the current in the secondary coil is lesser than the current in the primary coil. Hence, in a step-up transformer, the primary current is greater than the secondary current, but the primary voltage is what? Less than the secondary voltage. Another type of transformer decreases or steps down the primary voltage is called the step-down transformer. We have the step-up and step-down transformer. In this transformer, EP is what? Greater than ES, and hence LP is what? Less is greater than NS, and IP is greater than what? IS. So those are the differences between the step up and the what? Step down transformer. There are more turns in the primary coil than in the secondary coil, and more current flows in the secondary circuit than in the primary. The turns ratio is more than 1 for a step up transformer and less than 1 for a step down transformer. Don't forget that. The turn ratios is more than 1 for a step up transformer and less than 1 for a step down transformer. And this is an example. A transformer has 1000 turns in its coil, in its primary coil, and 3000 turns in its secondary coil. 30 volts is applied across the primary coil. What is its output? So we can get that because Vp over Vs is equal to number of turns in primary divided by number of turns, and when we do the normal calculations, our Vs is equal to 90 volts. Energy losses in practical transformers: one by eddy current. Such current produced by the varying flux cutting the iron core reduce efficiency because they consume power from the primary. Energy is lost in the form of heat in the iron core due to eddy current. Such loss can be induced by laminating the core. It can be reduced by laminating the core. The laminations of core induces eddy cutting by breaking up their path of flow. Hysteresis loss is wasted energy due to reversing the magnetization of the core. The core is made to go through a cycle of magnetization during each alternating cycle of the primary current. So I square R, or heat loss, because of primary or secondary coils have resistance. So energy is lost in the form of it. These are just different heat losses. This heat loss can be reduced by using thick wires or low resistance coil. Leakage of magnetic flux. So energy is also lost due to leakage of magnetic flux. This arises because of not all lines of induction due to the current in the primary coil pass entirely through the iron core to the secondary coil. through the iron core through the second. So power transmission. Power generated at power stations are distributed over large distances to consumers through metal cables. Power is given by P is equals to IV and can thus be transmitted either at low current and high voltage or high current and low voltage. Because the metal cables through which the power is transmitted have a certain amount of electrical resistance, transmitting power at high current will lead to loss of energy in the form of the bit of the cables. That's power transmission. To avoid this, power therefore transmitted at high voltage and low current. This is known as high tension transmission. So to avoid this, power is therefore transmitted at high voltage and low current. Low current leads to low energy and loss in the form of harm. Also, since lower currents require thinner cables, cost of cable materials is considerably reduced if power is transmitted with low current and high voltage. Step-down transformers are used to reduce the high transmitted voltages to low voltages required in homes and factories. What are the advantages of AC over DC? In power transmission, AC is preferred to DC in high tension transmission because the AC can easily be transformed to high voltages with very low energy loss. AC voltages can be stepped up or down by transformers while DC voltages cannot. A transformer cannot, of course, be operated with a DC because as soon as the current has attained a steady value in the primary coil, there is no change in the magnetic flux in the coil and therefore no induced EMF in the secondary coil. DC would require the use of motors and dynamos in order to produce a voltage change. This will bring about greater power losses than when AC is used, and those are the advantages of AC over DC. The induction coil. This is an electrical device that is capable of producing very high intermittent EMF by electromagnetic induction. So we've talked about the induction coil. Since a primary coil, it consists of a primary coil made up of few turns of insulated thick copper wire wound on a laminated soft iron core. The lamination of the core is to reduce losses of energy due to what? Eddy current. Don't forget that the lamination of the core is to reduce loss of energy due to eddy current. Secondary coil also, it consists also of secondary coil overlapping the primary coil. The secondary coil is made of large number of turns. Have you seen the difference of insulated thin wire? In front of the soft iron core of the primary coil is a mate and break device consisting of soft iron armature carried on a light brass spring to which is attached a platinum contact with adjustable screw. And that is about the induction coil. That's all about the induction coil. Thanks for this beautiful class. See you in our next class.